Hi guys, for today we are going to talk about lab exercise number 2, PLC ladder programming. A problem-based design, option A, which is traffic light system. So our group is consist of 3 members, which is me, Algo Chain Maria B, Alcantara Dever Roast, and Bigornia Frenchara Roast. For our objectives, we have 4. First is develop a PLC ladder diagram for industrial control. Second is to identify and map system inputs and outputs. Third is apply timers, interlocks, and sequencing logic. Fourth and last is to simulate and validate the system using PLCs. So this process focuses on the automated management of a dual lane intersection, ensuring smooth traffic flow while maintaining safety. The system is controlled using a PLC which manages the traffic light without manual intervention. In terms of the sequence of operation, the process starts with lane 1 having a green light while lane 2 is red for a fixed duration, allowing vehicle in lane 1 to pass. So after that, lane 1 switches to amber, which serves as a transition state while lane 2 remains red. This warns the drivers that the signals is about to change. Once the transition is complete, lane 2 turns green while lane 1 turns red, allowing traffic to flow in the opposite direction. So for safety, the system includes red clearance intervals and software interlocks. This prevents both lanes from having green lights at the same time, reducing the risk of accident. So this slide shows the input and output mapping of the PLC system. So input and output mapping is important because it links physical devices such as push buttons and traffic lights to specific PLC addresses so that program can control the hardware correctly. For the inputs, we have the PB start, which starts the system and is assigned to addresses 10.0, and the PB stop, which acts as an emergency or stop button and is assigned to 10.1. For the outputs, L1 red controls the red light for lane 1 at Q0.0, while L1 green controls the green light for lane 1 at Q0.1. So lastly, L2 red assigned to Q0.2 controls the red light for lane 2. This proper input and output mapping ensures that when the PLC logic runs, the correct light and buttons respond as intended, making the traffic system reliable and safe.
For our logic design strategy, we focused on making the traffic light system organized, safe, and easy to control. First, we use cascaded timers. These are TON or on delay timers that activate one after another. Instead of everything happening at once, each timer triggers the next phase, such as green, then yellow, then red. This helps ensure that the traffic sequence follows the correct order every time. Next is interlocking. We use normally closed or NC contacts so that when one lane is already on green, the other is automatically locked in red. This prevents two lanes from having green lights at the same time, which is very important for safety. Lastly, we applied latching using SR or RS coils. Once the start button is pressed, the system stays on even if the button is released. This avoids accidental shutdowns and keeps the system running continuously unless the stop button is pressed. After completing the logic design, we move on to simulation and validation. We tested our program using the CodeSys ladder simulation. This allowed us to run the logic virtually without using actual hardware. During the simulation, we carefully check if the system correctly transitions through all 4 phases: green, yellow, red, and the red red overlap. The overlap is important because it ensures there is no moment when both lanes are unclear or unsafe. We also tested fault handling by pressing the stop button. When this button is pressed, all outputs immediately turned off. This confirms that the system responds quickly during emergencies and prioritizes safety. In this project, we were able to apply important PLC logic concepts, especially sequential control and timing based transitions. One of the main challenges we faced was managing the timing overlap. We had to make sure there were no dark intervals or moments when no traffic lights were active. Solving this required careful timer coordination. This project is important because the same logic is used in real world urban traffic systems and industrial automation. A small mistake in logic can cause serious safety risks. For future improvements, the system can be enhanced by adding pedestrian buttons, sensors, or even smart timing that adjusts based on traffic density. To highlight the key learnings from this project, we identified several important points. First is I/O identification. Before coding, it is essential to correctly map physical devices like buttons and lights to PLC memory addresses. This prevents wiring and logic errors. Second, timers plays a critical role in industrial systems. They ensure that processes happen in the correct order and for the correct duration. Lastly, safety is always a priority in PLC programming. If a sensor fails or a problem occurs, the system can be designed to default to a flash red or all red state. This helps prevent accidents and keeps both drivers and pedestrians safe. Overall, this project helped us understand how PLC logic supports reliable and fail-safe control systems.
So, hello everyone. Now I will explain the ladder logic of our alternate per lane traffic signal system. So, first, the system operates only when the run mode is active. This acts as the main enable for the entire program. So, if the run mode is off, none of the traffic lights will operate. So, here is our ladder logic. So our ladder logic uses run mode, timers, and interlocks to create a safe and organized alternating traffic signal system. Now, atong i-run ang amo ang PLC ladder logic. So, pag-start pa lang sugod na dayon og count ang line 1 green light. Pag humana na niya, dire siya gauna. For the line 1, mag-una og on ang green light. Then pag mahuman na ang time for this L1 green light, mo next na dayon siya sa yellow light for line 1. And while line 1 is in green light, ang line 2 is on red light. Ano na to? O, diba? Nag-switch na siya into yellow light and then also yellow light for the line 2. Then after, nag-red light na siya for line 1 and green light for line 2. So before programming the PLC, it is essential to properly identify the inputs and outputs. So our system uses interlocks in ladder logic to maintain safety. Interlocks prevent conflicting actions from happening at the same time. In our project, interlocks ensure that only one lane can receive a green signal at any moment, preventing traffic collisions. Although our design does not use SR or set reset latch, it is important to understand when it is appropriate to use one. So an SR latch is used when a condition must remain on even after the activating input is removed. So for example, in a traffic system, An SR latch can hold a green light on until the reset condition, such as a timer expiration, occurs. So timers are a key component of our system. They control how long each lane stays green before switching to the other lane. Timers ensure smooth sequencing and fair traffic flow by giving each line a fixed amount of time to move. One important safety feature in our design is that both lanes can never have green signals at the same time. This feature is critical because it prevents accidents and ensures orderly traffic movement. So a potential failure in our system is a logic error that could activate both lanes simultaneously. The PLC prevent this by using interlocks that block one lane when the other is active. If the system needs to scale, such as adding more lanes, additional inputs, outputs, timers, and ladder rungs would be required. The same alternating logic can still be applied. So to improve program readability, we redesigned some rungs by separating timer logic from signal control and adding clear labels and comments. If a sensor fails by staying always on or always off, the system may behave abnormally. PLC logic can handle this by adding time limits, fault detection, or default save states such as reverting signals to red. So lastly, if multiple inputs are triggered at the same time, the PLC follows the alternating logic. One lane is allowed to proceed while the other waits, maintaining safety and proper sequencing. So, in conclusion, our alternate per lane traffic signal system demonstrate how PLC logic, timers, and interlocks work together to create a safe and reliable traffic control system. Thank you.